and welcome to Algebra II with Mr. Clausen. Today I want to talk with you about rational exponents, and specifically I want to talk a little bit about how you can switch between radical expressions and converting them to situations with rational exponents or vice versa. And then I want to go over a number of examples where we can multiply expressions with rational exponents in situations where they are made up of constants, maybe a single variable, or multiple variables, and show you how these can be applied to certain contexts. So to get started, I just want to look at a simple situation where we have the 1/2 power of 36. And we talked about this in the first lesson of this section, where when you have a value that is taken to a fractional power, the denominator of that fraction represents the index that is put on a radical sign. And then whatever is being taken of that power is the radicand of that given unit. So whenever we look at something like the 36 value to the 1/2 power, what we can do with that is that we can simply rewrite it given the shape of this specific format. And what it allows us to do is it allows us to think about radical expressions in terms of rational exponents. And this can be a little bit easier to analyze and even manipulate and do certain things with. Because the thing is maybe 36 to the 1/2 power doesn't click right away, but once it does, I think this will be a really easy way for you to interact with numbers or even punch it into your calculator. Well, we know 36 is a perfect square and that this would be equal to 6. And it can be a really simple way to look at it. Another context where we might see the same thing is that we have a situation where we have 4 to the 1 1/2 power, or 4 to the 3/2 power. And this is kind of a unique situation as well. And this circumstance, again, we have the denominator, which would indicate the index of a radical expression, but then the m value would indicate the power applied to the radicand. So in this situation, we can apply it to a similar situation here where we could go the square root of 4 to the 3rd power. And then this could be simplified out in a couple different ways. Maybe the easiest way to break this down is that if this is a square root, we can say 4 squared times 4. We can pull out the 4 squared. We can say 4 square roots of 4. We know the square root of 4 is 2, so 2 times 4 is equal to 8. Okay, and this just gives you an idea how we can switch from these rational exponents to radical expressions or vice versa. And the fact of the matter is there's a lot of different exponent relationships. It might be worth pausing this video for a minute and writing these down. These are all the different rational exponent relationships that I can think of. I put them all in kind of one place here. And if you're allowed to have a note card on your exam or a cheat sheet, write all these down. These are all different exponent relationships that you can use, plug in your calculator, use in various ways to find rational values that you can use in terms of radical expressions. So with that said, let's go try a couple of these examples out and see how they can be applied. So if we are looking at expressions made up of constants, let's look at a situation where we have 10 to the 1/2 power times 10 to the 1/2 power. Again, we talked about this circumstance where we said that the denominator of the power indicated the index of the root. And this could be viewed simply as the square root of 10 times the square root of 10. And we know the square root of itself multiplied by its square root will equal 10. Another way that we can look at that circumstance is that both of these have the same value taken to the same power. So if we look at it in terms of this format, we can say that this is equal to 10 times the 1/2 power plus the 1/2 power, and 1/2 plus 1/2 is 1, and 10 to the 1st power is simply 10. So again, a simple way that we can go and take something that's maybe a little bit more complicated and make it simpler. So again, another circumstance where we can use this is that situation where the base is the same for both numbers, but the powers are different. And again, you could try to go and take the cube root of this, and you could square this and take the cube root of that, and then multiply all those together. But the fact of the matter is that if you acquaint yourself with these rational exponent relationships, we can see very quickly that a example like this format arises, and we can see that the powers for these two values here can be added because they have the same base. So we can say 10 to the 1/3 power plus the 2/3 power is equal to 10 to the 1st power, and again would equal 10 just like it did in 10 to the 1/2 times 10 to the 1/2. So some useful stuff to keep in mind there. And certain relationships can apply if the powers match. So if the powers match but the bases don't, there's also a relationship with that where we can take these rational exponents and simplify them out a little bit. So we see a circumstance where a to the nth power and b to the nth power is the format that's here. And what we can do is we can actually combine these together under the same power. And if you think about it, you've done this before. This is the same thing as the square root of 3 times the square root of 12. And we know these are commutative, that you can combine them together and say the square root of 3 times 12. So all these rational exponent relationships are doing is showing you the same things that you've done with radical expressions, and now showing you how to do it with rational exponents. So in this given situation, they have the same power, so we can go and combine 3 and 12 to equal 36, and take that to the 1/2 power, and go the square root of 36, which would be equal to 6. And again, this would also give you the square root of 36, which would be equal to 6. And you can just go and find these values accordingly in a format that's much easier to enter into your calculator. So now let's look at some expressions made up of a single variable. Okay, so we have a constant and a variable that's present in this given example. And one of the things I want to point out is this kind of fits into this a to the m to the nth power, and whenever this occurs and you're multiplying powers together, they just multiply together. So in this given context, you would apply this 1/3 power to both the variable component and the constant component. So for example, we would go negative 27 to the 1/3 power times x to the negative 9th to the 1/3 power. And what we can do with this is that negative 27, if we take the cube root of that, looking at our previous examples, one of the things I can tell you is that the cube root of negative 27 has 3 negative 3's that make it, so this is equal to negative 3. And you could even plug that into your calculator in this exact format and it would give you negative 3. And then x to the negative 9th, well, this is x to the negative 9th times the 1/3 power. Well, negative 9 times 1/3 gives you x to the negative 3rd. But one of the things I want to point out here is that mathematicians don't really like these negative rational expressions. So what you can actually do is the negative value just represents the inverse. So if we say x to the negative 1/3 power, this is the same thing as saying 1 over x to the 3rd power. So now what we can do is we can take these two parts that we solved individually and we can rewrite it in this singular format, negative 3 2 over x to the 3rd power. And again, rational exponents allows you to look at these expressions in a much more quaint and simplified way so that you can go and rearrange them and simplify them accordingly. With that said, let's look at another example here where we have x to the 3rd power over x to the negative 1st power. And one of the things that you could do is that we could go and just take that negative 1/4 power and apply it to both the numerator and the denominator here. But I want to encourage you to do something first here. So whenever you see this circumstance arise, one of the things that you can do is that when you have x to the 3rd power divided by x to the negative 1 power, is that we can actually apply this variation first, where you take the power of the numerator, which is the third power, and subtract it by the power of the denominator. So we can go x to the third power minus -1 and see that this is equal to x to the fourth power. And I like doing this because there's a lot of situations in math textbooks where they'll go and they'll make it into this really convenient power if you follow this step. And now if you see x to the fourth power to the -1/4, if we follow this circumstance, -4 over 4 will be x to the -1 power. Again, if we're looking at this circumstance, just know that this is going to be equal to 1 over x, and that this would be your final solution given this circumstance. Now, the last example that I want to talk about here are expressions made up of multiple variables. So I have x and y that's present here. And I made a couple examples, and I want to do a really similar circumstance here. So if we have x to the 1/4 power and y to the -3/4 power, I think I will do the situation where I just distribute the 12 to both of these circumstances. There's no reason to combine them right away. So in this given case, I'll have x to the 1/4 power times 12 and y to the -3/4 power times 12. And in this situation, I'll see that 4 goes into 12 3 times, and 4 goes into 12 3 times. 1 times 3 will be x to the third power, and -3 times 3 will be y to the -9th power. And very quickly we took kind of a gross looking radical expression with rational exponents and simplified it out. And now the last thing that I do want to mention here that I would want you to do is let's not keep this negative rational exponent here. Let's apply this situation to it. Now, if you have a negative exponent in the denominator, well, if you had 1 over 9 to the -9th power, we're just going to take the inverse of it. So this would be equal y to the 9th power. So we can rewrite this expression as x to the third times y to the 9th power, and this would be the final answer that you would get for this. And this makes sense. 3/4 of 12 is 9, and 1/4 of 12 is 3. So another circumstance, let's look at this one. Now, I wouldn't quite go crazy distributing the 12 to everything here. And the reason is, as I see I have both y's and x's in both the numerators and the denominators. So what I'm going to do, just for simplicity's sake here, is I'm going to separate this out, x to the -1/2 over x to the -3/4 times y to the -1/3 divided by y to the 1/2. And this whole thing to the 12th power. So what I'm going to do is I'm going to apply this format to it where we have a to the nth power to a to the nth power, and this is equal to a to the m minus n. Okay, so we go x to the -1/2 minus -3/4, and here we have y to the -1/3 minus 1/2. Now you might have to match up some denominators here and do a little bit of work. So for example, -1/2 would be equivalent to -2 over 4. And if we look at 1/3 and 1/2, we could say that -2 over 6 is equivalent for 1/3, and -3 over 6 is equivalent here. And we can use that to our advantage to rewrite these given expressions. So -2 over 4 plus 3 over 4 would create a new expression here where we would have x to the 1/4 power, and -2 over 6 minus 3 over 6 would be equal to y -5 over 6, all to the 12th power. And then once you get to this circumstance, we can just distribute that 12, just like we've done before, or as is described in this circumstance, to both of these terms. We know that when we do this multiplication, it'll just be 1/4 times 12, which would be equal to x to the third power. And if we go 12 times -5/6, well, we can cancel out the 12 with the 6 and say that 2 is remaining, and then we get y equals -10. So it's just 12 times -5/6. Okay, and remember that y to the 10th power, that's just this circumstance here. This is equivalent to 1/y to the 10th power. So we can go and we can take again these more complicated rational expressions and then rewrite them as such to create new simplified rational expressions. So with that said, I hope you feel like you have a better understanding of rational expressions and how to manipulate rational expressions. And with that said, let's do math.